Hi folks, welcome back to Approximating Area, part 5 of the video. I should probably drink all of my coffee before I make these videos, maybe then I can actually speak clearly. But here we are. So question number 7. This number 7 says, find the integral from 0 to pi of sine x dx. Okay, so in line with all of our other color coding, let's stay consistent. I'm going to be starting at 0, I'm going to be finishing at pi, and the function that I'm interested in finding the area of is sine of x. So let's go ahead and start actually this time with dividing the intervals. So from 0 to pi, I want 4 intervals. So the top number is my b, the bottom number is my a, and that formula I said we could use last time is b minus a over n. So we've got pi minus 0 over 4, or each division will be every pi over 4. Okay, so that's how that equation works. So I'm going to start here, and let me make a table. So x, y, at 0, let me do it sideways actually. Okay. X, y, at 0, sine of 0 is 0. At pi over 4, sine of pi over 4 is square root of 2 over 2. At pi over 2, the sine of pi over 2 is 1. At 3 pi over 4, the sine of 3 pi over 4 is root 2 over 2. And when we get to pi, the sine of pi goes back to 0. Okay? So if you haven't caught on by now, knowing your unit circle for situations exactly like this is really helpful. Okay? So make sure you know that unit circle. All right, let's plot these points. 0, 0, pi over 2, root 2 over 2 is about 0.8666. No. Root 2 divided by 2 is about 0.7, so that point's a little bit high. So 0.5, 0.6, 0.7. Pi over 2 is 1. 3 pi over 4 is about 0.7 again, and pi is at 0, and so here we've got the top part of our sine graph. Okay, and let's make the subdivisions. So here, 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 okay. And we used red for our RAM, and we used orange for LRAM, and what color did we use for trapezoidal head? Blue. Okay, so trapezoidal. And remember, we're leaving the MRAM out of this just because it's really hard to tell, is it exactly above and below? And so these are the 3 main ones I really want us to pick from when we're exploring over versus under estimates. So let's draw those y values. We'll circle them in the appropriate colors. So our RAM would mean I would want this, the right endpoint, the right endpoint, the right endpoint, the right endpoint. Okay. And the left one would be the left endpoint, the left endpoint, the left endpoint, and the left endpoint. Now in this case, you might notice that it's actually symmetrical. So the right one and the left one in this case happen to be the same. Now if I draw a left one just to kind of give us an idea, that would be like a rectangle like this. And this one would be like a flat line. So I'm thinking LRAM is going to be an underestimate because I have one that's missing like this whole big chunk. So let's put LRAM in for an underestimate. Now our RAM, if I draw a few of those, well, this one looks like it's going above that's not an RRAM. RRAM, sorry, would be like this one right here. That's going to be too flat. This one. Okay, so maybe I'm thinking RRAM is also an underestimate. Okay? Now keep in mind though, this one is probably a little harder to tell because RRAM for this one goes way above. But does that cancel out the one where we got nothing? I think the nothing one actually is more than what it goes over here. So that's why I'm going to say LRAM and RRAM are underestimates. And in this case, I would actually say that we don't have one that does an overestimate, okay? But the trapezoidal, let's take a look at that. So if I go ahead and take a look at the trapezoid, I'm going to go ahead and erase what I have here so that the diagram doesn't get too cluttered. Okay. And let's get those points back in there real quick. And I've got my 4 subdivisions. Okay, let's see what the trapezoidal one looks like. So I would connect here to here, here to here, here to here. Yeah, they could be slanted in both directions. It doesn't really, they don't all have to slant in the same direction at the top. You just have to connect that endpoint to this endpoint. Okay? And when I look at these, I think trapezoidal is probably the best approximation, but I also think that it is a touch underneath the actual curve. Okay? So in this case, all of them are looking to be an underestimate, and that's okay, all right? But let's figure out what our exact area would be. So we've got the integral from 0 to pi of sine x dx. So what function has a derivative of sine? And I know the derivative of cosine is negative sine, but I want positive sine. So that must have been negative cosine. The derivative of negative cosine would be negative negative sine, which is positive sine. I'm going to draw the bar. Instead of putting a plus c, my starting point is 0, that goes on the bottom. My ending point is pi, that goes on the top. I'm going to plug in the top bound, so negative cosine pi minus the bottom bound, minus cosine of 0. So here again we see that we need our trig values to finish the problem. Cosine of pi is negative negative 1 minus negative cosine of 0 is 1. And we need to be super careful about our signs here. We've got a positive 1 plus 1, which gives us an area of 2. So each of the bumps in sine and cosine actually have a perfect area of 2. And I know it's weird because it looks kind of like maybe it wouldn't be an exact number, but every bump has an area of 2. So we could even say, if I drew out like the whole sine curve, that this area would be positive 2. If I'm going in this direction, this area would be negative 2. Okay? But if I were going in the opposite direction, like this way, okay, this would actually be positive 2, and this would be negative 2. So again, that's just a reminder that the direction that you count in actually matters. Okay, so let's take a look at question number 8. So this is a good way that I want you to think about synthesizing all this information, okay? So in this question, I'm asking you to draw your own scenarios. So let's take a look at the scenarios. Part A, sketch a graph where a trapezoidal approximation with 4 subdivisions would give the exact area between the curve and the x-axis. And I want you to set up the approximation, but I don't want you to solve it, okay? So let's take a look at a potential graph. Well, if I want the trapezoidal approximation to be exact, that means that I want maybe some sort of slanted top, And so a nice simple case that I could think about, and here let's make this all positive to make it just a little bit easier to think about, is I could have something like this. And then if I cut this into 4 subdivisions and I connected the tops, everything would be exact. Okay, so that could be a good example. What I mean by set up the approximation is I want us to say, well, I know the formula for a trapezoidal approximation is height over 2, and then 1 f of a, which is the first one, plus 2 f of all the other ones, plus at the end I want 1 times f of b. Okay? So I'm going to call this A, f of A, and this one will be B, f of B. And my height here is going to be B minus A over N. That will give me my height. Okay? So I know this is really abstract, but I'm asking you to apply sort of the concepts of what we're doing here. Okay, so my approximation would be 1/2 times B minus A over N, which is 4, times, let's say, f of A plus 2 f of the next one plus 2 f of the next one plus 2 f of the next one plus f of b. Okay? And you could give this point, you could call it like C, f of C, D, f of D, E, f of E, and that would be okay. So you could say 2f of C, f of D, f of E, okay? So again, it's focusing mostly on the concept and less about the actual numbers. All right, let's take a look at part B. Sketch a graph where LRAM with n equals 4 gives an underestimated area. All right, so let's see. I want an underestimate if I use the left. So I'm going to have one that maybe looks like this. And I'm going to cut that into 4 equal, well, they're supposed to be equal, don't judge. All right, let's call this one A, f of A. This one will be B, f of B. And we'll call this C, D, and E like we did in the last one. And so your left estimates would give you ones that are underneath that, okay? So underneath. All right, so for LRAM, our formula is going to be the base, which is B minus A over 4 times f of A plus f of B plus f of C, C, D plus f of E, and there's no f of B because we don't actually use the last endpoint. Okay, last one here. Sketch a graph where RRAM with n equals 4 would give you an overestimate. So I'm actually going to draw the same picture, right? I'm going to divide that into 4 equal pieces. Again, we'll call this A, B, and then C, D, and E. And if I did a right estimate, I would end up with things that were taller than my graph. And let's see which values we used. B minus A over 4. We didn't use f of A, but we used f of C plus f of D plus f of E plus f of B. Okay, so all of these are the right endpoints, and all of these ones are the left endpoints. All right, we'll stop it here for part 5 of the video. See you back.